So the first speaker is Professor Chao Wang from Peking University. The title of his talk is The Local Well-Posedness of the Water Wave Equations. So please.
Okay, thanks for the introducing, and I also have to thank all the organizers for giving me a chance to give a talk here. I can, of course, this is a good opportunity to discuss with all the experts here. So I think I will learn a lot from this workshop. Today, I will talk about the local well-posedness of the water wave equations. This is my program for this talk. I will explain it line by line. And here we just to look go to the equation, the water wave equations. So actually, this water wave equations is described by the Euler equations. This first line here is Euler equations, and the second line is things that this equation, this flow is incompressible. Of course, we to simplify the equations, we sometimes we can assume the fluid is not a rotation. The problem is different from the classical Euler equations because the boundary will move and the boundary will change when the fluids move. So when we solve the we have to solve the boundary here. So there's another boundary condition come out is for the pressure. Here we can assume that pressure is equal. Okay, and then we think that I draw a graph for this domain. Sometimes we can assume that this is gamma t, this is gamma b. Gamma t is movable, gamma b is fixed. So we also assume that the surface is gamma t, the bottom is gamma b. This is a very we have to add the condition that the pressure here is have the equal to the sigma kappa. Sigma is a constant. It's we call it the coefficient, the surface tension coefficient. And the kappa is the mean curvature of the gamma t. So of course we can assume that sigma is equal to 0. That means that the fluid is without surface tension. When the sigma is positive, this means that this fluid have surface tension. Of course, we have to assume that this material derivative pi t plus v dot gradient is tangential to the gamma t. There's when we assume the boundary condition for the gamma t, we use a very classical boundary condition. That means v dot n b equal to 0. This is a classical water wave equations. But today we will focus on another problem. That means we assume that this is gamma b, this is gamma t. That means gamma t is touch the gamma b. This is so we assume that this angle is omega L. Here is omega r. So from this graph we can find that this domain has singularity. So this is difficult. This is the most difficult part. So we have to deal with that. Now we give the equation for this model. So actually, the most of the equation is the same. Here, from the first line is the Euler equations, Here is means the second is incompressible and in rotational fluid. The only difference is means that we add some things, add some boundary conditions on the contact point. This means we add some, we need some condition this on this point and this point. Okay, I have to say that here we will focus on the two-dimensional. So if you can, of course, you can consider the three-dimensional case, but we will talk about later. We have to say that here we assume that the fluid is have the substantial. That means sigma is positive. We have to point out if the sigma is sigma to 0, we don't need this boundary condition on the PI. So okay, this is a big difference between the this model. Of course, if this condition on the PI, we just to use the it's come from the very stationary. Of course you can add and you can use the other boundary condition on the PI. We will explain that later why we use this one. Of course, the condition on the PI is if you use the material derivative is tangent to the gamma t, we can change the boundary condition on PI to this one. This is the same. Of course, if you can, if you assume that this is fluid is steady, so the condition will become this one. All things will begin the equation WW, the system WW will reduce to this one. So, of course, if we from here we can see that the kappa is two directive on the eta. Eta means okay. I have to say that the eta we can assume that this free surface is graph means y equal to eta, something like that. So we can see that this is elliptic equations. So if you want to solve this elliptic equations, we have to add the boundary condition on the PI. That means if you this is a boundary condition on the PI is necessary. Of course, you can find here that if the sigma is to 0, that means this term we are vanish. So we don't need any condition for the any condition on the PI. Okay, from this point we can see that this is a boundary condition on the PI is necessary. Okay, so let's mention some. Let's go back to the water wave equations. So we want to solve this system WW, but if you before we state our results, we mention some results on the classical water waves. So here we call the classical water waves. This means that gamma t does not touch the gamma b. So to study the classical water wave equations, one key point is that we have to study directly Newman object. Here this operator we denoted by J eta, which is defined by J eta c equal to this one. It seems very complicated, but it's very easy to understand. It's come from here by this one. here we consider the elliptic equations with the directly boundary conditions, just like here, Laplace phi equal to 0, phi, the boundary condition on the phi is C. So this is, of course, we can solve this elliptic equations, but we need another one. We need this one, gamma y equal t. This means when we solve this elliptic equations with directly boundary conditions, but we have to calculate the Newman boundary condition for this elliptic equations. This means we this is almost equal to the just we denote like here. This means then we call it directly Newman object here. Of course, some guys will ask why did this one. This one is normalized this object, so it doesn't bring any trouble. So it's just to look at this one. Okay, when we introduce the directly Newman object, we can rewrite the water wave equations. Here we can use for example, we can use the Zakov-Craig-Solis formation. That means we can reduce we reduce all the quantity to the free boundary to the gamma t. That means, for example, we introduce the psi is equal to the phi. The psi is equal to the boundary condition of the phi on the gamma on the free surface. Here, the phi is vorticity potential functions. That means v equal to gradient phi. Of course, here this we have to assume the fluid is interrational. Okay, if not, we can use other formation, but here we just to state the most difficult of the system. So when we down here, we can take the trace of the free surface, the system. Actually this Euler equations can be reduced to this system. This system looks like very complicated, but here we can find that this. Because we reduced all the quantity to the free surface, so the variation xh here is belong to RD, is belong to the whole space. So that means that if you consider this system is defined on the whole space. So there's no boundary here. So that means we can, when we consider this system, it seems that everything maybe become easier. And the only difficult things here is that the directly Newman operator just you can find here and here. So that means that if you can learn very well of the directly Newman operator, so you can know this system very well, and so this is so when they study the water wave equations, at least if you consider about the local hypothesis, the system, so consider local hypothesis, the key point is that to study the directly Newman operator. So okay, that's many formation for the water wave equations. Others can use the Lagrange coordinate, geometry structure, and many other formations. So here we don't expand everyone. So So let's go back, go to some known results of the water waves. So that's actually by now, I think when you start, when we consider about the classical water wave equations, I think the structure of the classical water wave equations is very clear. But the breakthrough is given by the Sijue Wu in the here, and after her work, there's a lot of other works come out. So use a different method to study the water waves, and okay, just like as I said before, the key point to study the water wave equations is to study the Dirichlet-Neumann operator. And on the global hypothesis, that's also the first result is given also by the Wu, and after her work, there's a lot of other works come out and to consider many different case of the water wave equations. Here I have to point one important thing is that when we consider about the classical water wave equations, the regularity of the velocity is that v belong to hs. S is bigger than 1 plus d minus 1 of 2. This means the dimension of the free surface. Of course, here I write the minus. That means if somebody use that means that the first result is given by the Alza-Buick-Zuni. They use the structure estimates. You can reduce. You can get the very improve the regularity of the velocity. That means they need a they can get the water wave equations in a well-posedness in a very low regularity space. Okay. Actually, this means but after that works, that's a lot of some guys I didn't to write here. That's some others were good jobs to work on the classical water waves. Now we go to the non-smooth water waves. That means here we consider that the gamma t is touch the gamma b. For example, here, the first result is given by the Alza-Buick-Zuni. They consider the case that the contact angle is equal to pi of 2. That means that they use this case. Then they use reflection. That means that here they use this one. So actually, they can prove that without a substantial, the angle, if the initial contact angle is equal to pi of 2, then the angle is equal to the pi of 2 for all time. So they use the reflections. So that means from here we can see if the surface is still smooth, so they can go back to the very classical ones. The breakthrough is given by the also by the Wu, the same guy. Her proved that he proved that he can use this ones. That means this is boundary gamma b. Gamma b is just this ones, and in her setting that. He proved that if there's an angle here, there's an angle is less than pi over 4. He can prove the local hypothesis. So this is the first result on this case. But in her setting, that the angle cannot change. Cannot change. This means that the initial contact angle will not change with the time. And recently, Kotoba, he proved that this angle can be changed if we don't consider about the gravity. Okay, I'm sorry. And recently, this guy, T-Ball, he can prove that he considered this case, just like this case. He proved that he gave a priori estimate for the water waves with emerging boundary, and in her setting that this of course he considered the water wave without substantial, and he gives the priori estimate when the contact angle is very small. I will explain why the angle is small later. Recently, Devinan, he considered floating body problems and give some toy model, and he proved some local hypothesis of this model. For more results on the moving contact lines, I think I have to mention that the school and ties, they consider stocks flows and level stocks flows, and they give a priori estimates and they give the long time behavior of this system. To my knowledge, that's another problem considered about the Darcy law that's given by the Masmoudi and Kung Fu. They proved that the global hypothesis for this system. So this is of course I think that's a lot other results on the contact angles, contact line problems. I think after my talk, there's a lot of very nice talk explaining more on that. Now let's see go to our results for the local hypothesis for this case. This is our first case. That means that if we assume the initial data, this is gamma t, this is gamma b. If the gamma initial the initial data gamma 0 and v0 belong to this space, then and the contact angles is actually we assume it's very small. You can. We will explain why this angle come from. If on these assumptions, we can prove that this system can be well-posedness. Yeah, actually, it's local well-posedness. Here we just say that the gamma t and the v. The pressure is given by the V and the mean curvature kappa. It's given by the following case. P is equal to sigma gamma h kappa h. Here we will explain later. This is PVV. Is PVV. This is kappa h means the harmonic extension of the mean curvature kappa. The PV is given by here. This is by this elliptic equations. That means if we as long as we have the gamma t and the v, we can get the water wave system is recovered immediately. Then here let's give the outline of our proof. As I said before, that when we study the water wave equations, we have to study the Dirichlet-Neumann operator. Here we can find that because we assume the gamma t can touch the gamma b, that means the elliptic equations is defined on the a domain which is not smooth. But here we can find that we don't if we as we know that if we consider about the elliptic equations in the ellipsis domain, it's very hard to get to a very good estimate, high order estimates for the elliptic equations. Fortunately, that's we only have we can in the domain is the corner domain. It's only have the singularity on the corner. Now we go to the elliptic equations in a corner domain. That's considered about in this case. That means Laplace u equal to h. Let's give for example, we join this graph here. This gamma b, this gamma t. Here on the gamma t, we give directly boundary conditions. On the gamma b, we give some Newman boundary conditions here. So even if the h, f, g is smooth, but we cannot get the u is smooth. So so this is a big problem. So we forgot the water wave equations. We have to solve this elliptic equations in a corner domain. Fortunately, that's consider about this problem. There's a lot of work. The fundamental work is done by the Kodravic. After his work, there's a lot of work on that. Actually, we can find that we didn't mention it. There's a lot of so by their works. Actually, this elliptic equations we can get this very we learn this elliptic equation very well. We have this following singular decomposition. We can get that u equal to ur plus us. Ur means the regular part. This means that you can assume ur is as good as you want. But the singular part, us, is here. Us is we don't. For example, we cannot expect the us is smooth as you want, but we have almost the structure. We can describe the US very well. That means we can US looks like this one. That means US means u for example u alpha. The alpha we can give a very we can define the alpha very well. So that means that for the elliptic equations we cannot expect it's smooth as you want, but we can get the singular part, and we know the singular part looks like. Well, that's give us a computation to study the elliptic equations and use this theory to go back to the water wave equations. And here we can find that the alpha is just like here. Lambda m is belong to this case. Here that means that we have to assume that lambda m is belong to is between the -1 and 0. If the lambda m is not belong to this restriction, that means the single part is 0. That means so. That means that maybe the singular part is vanished. So we give some very particular some very some results on this elliptic estimates. So when we consider the H2 case, that's the low singular part. When this angle is belong to 0 and is belong to between the 0 and the pi of 2. But if you consider very regular single parts, consider hk minus plus 2. Then we have this following estimates for this one. So here we will, as I said before, when the omega is very small, for example, we don't, if we assume this beta equal to 0, this means this one equal to 0. So that means that when the omega, this omega means the contact angle is very small. So we don't have this m such that the lambda m is between the -1 and 0. That means the singular part is vanished. So that means that when the omega is very small, the singular part is vanished. So that means the elliptic equation is as we can get is as the classical ones. So this give me some. That's why T-ball and this why we assume here we have that we assume this our results. Our first result is to assume the contact angle is very small. This means we can remove of the singularity. Okay, but so that's explain how we do that. So by now we have if we assume this contact angle is very small, so we don't the elliptic equations don't have any singular part. So then we go back to the Euler wave equations. So first thing is we have to choose a good formation to describe the this is contact this problem. We call the beach problems. So here we use the geometry formation. This is first introduced by the Chata and Zen. That means we can use at first we can drive the we drive the mean curvature equations. We can use the Euler equations and the evolution of the gamma t. We can get the evolution equations for the kappa. So here we this term is we just work on this for gamma t. So we don't have here gamma t. We still assume this very small. So this formation is almost the same as the Chata and Zhen. Here we have to point that this I1 is a low order term. Then we bring the Euler equations to this term. We can get formation for this term. Then we can test this formation. So if here we have to point that R1 contains the term this one. This one we will explain why we point here because of this term we have to assume the contact angle is very small. So from here we can know that this formation. So if from here we consider we just to look at this one. This is just like wave equations. This is we just like this one. This is a wave equations. So we almost get the results. But here we have to point out that this is Laplace, but this wave equation is defined on this domain. This means we have when we study this wave equations, we need the boundary conditions. That's why we need the boundary condition. That's why we here we have to we need this boundary condition here. But if from here we can know that, okay, sorry. If we consider about the multiple equation without substantial, so the main part of this formation is that this term, this is dedicated Newman operator here. So that's when we use the energy methods, we don't need the boundary condition for. We don't need the boundary condition on the on the contact point. So this is easy way to start to understand why we need the boundary condition here. Now we give some details for the formation of the water wave equations. Here we have to define the harmonic extension. Here we need the on the gamma t, we need the boundary dedicated boundary conditions. On the gamma b, we need the Newman boundary conditions. So we don't work on the equation of kappa. We work on the equation of the j. J is defined by the gradient kappa h. Use this one because that we from the boundary condition of the pi we cannot get the boundary condition for the kappa. We only can get the boundary condition from the j. So that's we use the equation of the j. Of course, here the A is defined by this way. Actually, here we can find that this formation is the same as the classical ones. Of course, we have so we have to mention that I contains this term. This term we need the more regularity of the elliptic equations. So we need to restrict the contact angle is very small. So next we give the energy method. Give the energy estimates for this equation of the J. We give this first. We define the energy functions. ET is defined in this way. Here, this of course we have the dissipation on the contact angle. It's defined this way. So if we just to give the priori estimates, we don't need the contact angle is very small. We only need we can get the contact angle is belong to this class. How to do that? It's very easy because that's by now this is very classical ones. That if we multiply the dtj on the both sides of the equation of j, so we can get this formation here. So the main part of the here we have to work on this one. So by the definition of the operator A, we can use this one. Here we have to mention that the divergence is you use the integrated by parts, we can give these ones. So from here we can find the first terms. We can because this is Laplace, so we can integrate by parts again. But here we integrate by parts on the gamma gamma t. So that's also give that's why we need the boundary condition on the contact point. That means that if we integrate by parts here, this term will come out. So we need to calculate this boundary condition. Of course, we use the boundary condition. We can prove that this one is equal to this one. Of course, you can choose another boundary conditions. We just need this is this term is negative. of course, here is minus here, so this one is negative. Then we also can close the energy. So to my knowledge, there's many ways to propose the different boundary condition, define boundary condition on the contact point. Now we go back to let's go back to why we need the contact angle is very small. For example, we based on our energy estimates, we need this L2 norm of the R. L contains these terms. From here, that means we need PVV is belong to H4. So if we consider about this elliptic equations, if we don't want this elliptic equations, the H4 estimates of the PVV, we need the contact angle is smaller than pi of 6. Okay, this is why we need the small contact angle. Okay, based on the this is a very basic energy estimate. But if you want to get if you need to prove the existence of this system, we need some high order energy estimates. So, but we cannot. Here we have mentioned that we can, if you want to get high order energy estimates, you cannot take the directly, because if you can use this commutator, this is n is a Newman operate. This is plus. This is a one order term operate. This is one order. So usually this commutator is one order. But here we consider about this is this domain have the contact angle. So this commutator is still two order. So that means this is higher order terms. So this you can not. So if you take the partial x directly on the equation of the J, you cannot cross the energy estimate. But we can. So here we use the geometry spaces. We can add the A. This A is this means that we'll go back to the equation of the J here. So that means that we don't to act the partial x on the. This is not work. We can add the A on the both sides. This means you can continue. You can calculate this commutator. This one is good. This is a low order, but this one is not good. Or this one and this one is not good. So use this observation, we can we get the high order energy estimates. Then we can construct the approximate solution of the water wave equations. So that the next we give some details for the for constructing the approximate solutions. Because we have to use the first thing that we have to do is use a map to reduce our system to a fixed domain. So here we use a map is defined here. Phi st. I will give the definition later. So then use this map so we can reduce our system to a fixed domain. So then we can consider about this problem. So then we give a new new quantity. This means RA. Actually, this is almost like the J. It's almost like the J, but we have this term. That means that's the D gamma T means that this is gamma T. This is gamma star. This T, it means the distance between this distance between the two surface. So we have added some low order term. That means we can use the elliptic. We use to solve some elliptic equations. That means if we get the RA, we have to go back to the D. Okay. So based on the before the calculations, we can get the equation of the RA. Of course, the almost is the same. The only we have added some lower order terms. This doesn't bring any trouble on this problem. So when we define the I, we have to. That means from the RA we can define the d gamma t. So then we have to define the velocity. So velocity is defined by this way. V equal to gradient phi. Phi is defined by this elliptic equations. Here we can something that we are point at this term sometimes we is equal to 0 because we as our definition. If we use Euler equations, but here from the d gamma t we can define the phi. The d gamma t we cannot get this theta is equal to 0. So we have to prove that this one to 0. This means that from although we give the construct some approximate solution of the RA, but we have to go back to the Euler equations. That's some gap. So this is why we have to give some theta gamma here. Later we can assume that we can prove that it's equal to 0. This is the last part of our paper. So so by now, if the d gamma t can be defined, we have to go back to because we have to need some point because the curvature is given. But if you want to go back to the first surface, we have need some boundary condition for this first surface is given by this one here. So this system IDL DR provides a closed system to construct some approximate solutions. So okay. Then because here we need some the high order estimates, so we need this contact angle is more smaller. Okay, how we define the phi s means that if the gamma star gamma t this is gamma. Oh, I'm sorry. We can use this is the normal vector here, but with normal vector is lose some regularity of the gamma t, so we can modify this gamma t. We can use this one. This is very close to gamma nt, but it doesn't lose any regularity for the gamma t. So this is how to we define this math. So this is the key point of this this proof. So so then we will go back to the energy estimates here, because here as I said before, that we have a closed system, approximate system here. So we can then, based on these terms, we can give some higher order energy estimates here. So as I explained before, this from here we can know that if we want to get the high order estimates for the F, we need the more regularity on the G1. G1 is means a reminder. It's a, G1, for example, it contains the if you want to prove this G1 here, we need this one. That means that this system, we need this elliptic system. We need more regularity. That's we need the contact angle is smaller than the pi of 16 to avoid the singularity. This is the first results on the we prove the water waves in the corner domain with some small contact angles. But for example, then after that we have to consider about that when the omega is bigger. For example, omega is less than pi of 2. That means omega is close to pi of 2. How can we get the local well-posedness? Recently, Professor Zheng and Professor Ming and I, we proved that if the contact angle is less than pi of 2, we can prove this local well-posedness. So the first thing that we have to change the definition of the PVV. From here, with that with the PVV, the first thing with the this is a delicate boundary conditions. We change to some. Oh, I'm sorry. This is gradient. Sorry, Newman boundary condition here. So then, according to the theory of the elliptic equations, we can prove that PVV belongs to H3. But some guys, we can go back to the priority estimates. For example, we need this one term because this is a CVV is a constant. It's constant. It only depends on the time t. So this term is equal to this one. So that means that from here we can only that PVV we only need the PVV is belong to H3. So that means the regularity for the PVV is enough, even with the contact angle is smaller than pi of 2. So, but another bad term will come out in the remind terms. That means this one. For example, we can mean that this I explain 3 directives on the V. But according to the estimate of the equation of the V only can prove that V is belong to H2. So, but how to do with that? That a key observation that although the V is belong to H2, but DTV is belong to H3 of 2. That means that but from the structure of the water wave equations, it means that the one directive on the time t is like the 3 of 2 directive on the space. So although the V is bad, but the DTV is good. So that's the way we can. So when we work on the V, we need very carefully. We have to add some. We change the directive on the change the directive to the time directive, space directive to the time directive. So this is our key observations. But but we still have some. But we still have. That's not enough. But we still, when we calculate the energy estimates, we still need the singular decomposition of the V. For example, we have when we estimate we point out, we give the example of the one of the most trapped terms. For example, here, we forgot this one. Here, because this is too directive on the weight, we only prove that weights belong to H2. But this term, this means this term to -2. So that's bad. So when we to do that, that means that we can use this. T is the boundary condition, the boundary value of the J here. So we use the decomposition. This is a constant. This is, we can prove that the gradient V's belong to L infinity. So according to the elliptic equation, we can prove that V is equal to I, alpha. Alpha is bigger than 1 less than 2. So that means gradient is like this one. So when we integrate by part, so this term is -2. So this one is bounded. So how to do this one? This one we can use this. We just like we said before, we bring out this time t out to this one. So this one is L infinity. This is L infinity. So this is belong to L1. This is okay. For this term, we can do that. We integrate by parts again. So we can get that this one is belong to H1 on the free surface. So we use some boundary the singular decomposition of the wave. We can prove that this one is bounded, also bounded. So that's we can close the energy for the bigger contact angle. So this is a basic. All here do is a basic energy. So when we consider about the high order energies, high order energy estimates, to do that here we don't use act the operator A. We change to use we use dt. So, but dt does not bring any more space directive. That's very, very important observations. And based on that, we follow the before we can close the energy. So we also can get local well-posedness for the bigger angle. So that's all. Thank you.
Professor Chao Wang, thank you for your interesting talk. Are there any questions or comments? So I have one question.
Yeah.
So in your talk, you restrict the value of contact angle that is very, very small, such that the singular part will vanish.
Yeah.
How about using the weighted function spaces?
Weighted function space. Okay. Yeah. Here we at beginning when we prove we want to prove this contact angle, bigger contact angles, we want to use some weight function space, but here we can to see that. Okay. For example, we can see that. Okay. Oh, I can go back to the. Oh, we go back to the equation here. Okay. So. Okay. So okay. For here if you compute, for example, we can use the I space. I means the distance to the contact point. When we can take to calculate this one is not good. This is also high order terms, so we cannot close this energy. We don't know how to do that.
Okay, thank you.
Because of this operator is three order operator. But if you consider about the water waves without substantial, maybe it's okay. Maybe it's okay.
Okay, I see. Are there any? Okay. So Professor Azal, please.
Yeah.
Okay, thank you very much. My name is Jürgen Saal from the University of Düsseldorf. I would be interested in the necessity of this condition that the contact angle must be small. So as I understood, it comes from the well-posedness of related elliptic problems. But can you say something if it's really necessary, a necessary condition also?
Sorry, you mean the small contact angle?
Right, the smallness of the contact angle.
Okay, because when we study the local hypothesis, we need the high order energy estimates. That means we need more regularity for the elliptic equations. For example, here, we need the elliptic equation is belong to very high order, very good. For example, here we need this HM6 estimates for this elliptic equations. That means we need the small angle. But recently we can remove this one. Sorry, am I clear? Not sure. I'm not.
So it cannot be removed, you say?
Oh, as our first papers, we cannot remove this one. But recently, we can. We don't need this. We can. We don't need this estimates. We only need this belong to H3. Is enough. That means in my first our first results. That means we need too much regularity on the PVV. We can ask we can work on very no regularity for these terms.
Okay, thank you.
Thank you.
Are there any questions? So Professor Abels, please.
Yeah, hello everybody. I'm Helmut Abels from Regensburg. Concerning this equation F, which you had the second order time equation, which was basic for everything, but the type of the equation was not completely clear to me. So I suppose it's still hyperbolic, or is there maybe it is still even parabolic that you gain some regularity?
You mean the equation for the F?
Yes. So
for the F is harmonic, but that's some terms on the G1. If you want to estimate the terms on the G1, you need some elliptic equations.
Sure, but okay, so the F is really hyperbolic that you cannot expect some gain of regularity in positive time.
Yeah.
Okay. Yeah. Thank you.
Any questions or comments?
I'm Irina Denisova from St. Petersburg. I'd like to ask, may I ask?
So please.
Sorry, okay.
I'd like to ask about the setting of the problem at the beginning of your talk. Please. Maybe it's the first system.
You mean here?
Oh, at the beginning, yes, yes, it was that one. I'd like to ask about the number of equations and the number of unknown functions, and I mean that the number of equations more than the number of unknown functions. What about curl V equals 0? Maybe it's not necessary.
You mean here? You mean this is a condition here?
Yes.
Oh yes, you're right. If some you can remove these conditions. Yeah, yes, you're right. You're right. But we right now we want to symbolize this equations, this problem. So we add these conditions. Yes, you're right. We can remove this one. I believe it's also true for the for if we don't have these conditions. I believe that. Yes, you're right.
Thank you.
So okay, so let's thank speaker again.
Thank you, everybody.